Armed with this mysterious approximation using a bell curve, let us return to our application of poles. We have seen why poles have a principled justification via the law of large numbers. Our difficulty then was not that it didn't seem to work, but that the sample estimates were just a little uncomfortably too large for our tastes. So let's go back and take a look at it again through a new prism, through normal approximation, and see where it gets us. So let's review very quickly the model for a pole. We have an underlying population, which has got two subpopulations in proportion, say, P and Q, where Q is, of course, 1 minus P. P and Q are fixed but unknown. We want to estimate P, and we do this through the mechanism of repeated independent trials, where we sample at random with replacement from the underlying population. This engenders a sequence of Bernoulli trials, x1, x2, x3, through, let us say, xn, where each of these takes value 1 with a probability P and 0 with a probability Q. We form the accumulated successes by adding these x's. Our development has led us to conclude that it is reasonable to estimate the fixed but unknown P by the known but chance-varying sample mean Sn divided by n. Of course, the moment we make an estimate of a fixed quantity by a chance-varying element, then we make errors, and we can only make pronouncements with some confidence. We've seen how the error in the estimate, the confidence in our pronouncement, and the sample size all interact beautifully. Chebyshev's inequality tells us that the probability that our sample mean deviates from the underlying probability P in absolute value by epsilon or more is no more than the reciprocal of 4 times n epsilon squared. And we'd like this to be no more than some given small delta. We want a confidence of 1 minus delta that we don't make an error as big as this. And this leads us immediately to a very, very simple prescription. If n exceeds the reciprocal of 4 epsilon squared delta, then we can guarantee an estimate error of no more than epsilon with a confidence of at least 1 minus delta. And we saw that immediately, numerically, it gives rise to numbers like those you see on the screen. In particular, if we demand an error of no more than 3% in our estimate of P, and we want a confidence of 95%, then the sample size that is requisite is about 5,500. Now, that doesn't sound very much, especially when one is dealing with large populations of millions or even billions. But getting an estimate of even 5,000 individuals is laborious, time-consuming, expensive. We realize that this estimate is sufficient but might not be necessary. We might be able to trim some fat from this estimate. And the suggestion arises because of the inequality of Chebyshev, which is like a blunt instrument. We are taking a cleaver to cutting butter. In the process of making an estimate, an upper bound, the estimate perhaps was a bit too generous. And therefore, the sample size estimates then also become a little bit too large. Let us see where normal approximation leads us with this desideratum.